in Tuskegee. I think you guys are on the web app, not the the Windows app, and I think that's maybe why you can't share when you guys are doing that for future reference. All right, Team 3, floor is yours.
So good morning. This is Tyler from Clemson University. Thank you for being here for our critical design and production readiness review. We are Team 3 or Team Storm. We are comprised of students from Clemson University, Georgia Tech, and Tuskegee University. So to open, we would like to provide everyone with a brief overview of our mission, which is to design a vertical takeoff and lift capable UAS that can identify disaster victims and provide them with preliminary aid. In addition to vertical takeoff capabilities, which will help us better access disaster areas, we're planning on implementing a camera for surveillance purposes, as well as an accurate payload drop. Our key performance indicators dictate that our UAS will maintain a approximately 30-minute flight time with a 17.5-mile range and will weigh roughly 12 pounds. So here is an overview of our team structure. We have 6 integrated product teams, which include aerodynamics, led by Prince Johnson at Tuskegee University, CAD, led by myself and John Knobloch here at Clemson, controls, led by Jen Tano at Georgia Tech, manufacturing and integration are combined into one team, led by Andy Person at Georgia Tech, propulsion, led by Aaron Dorsey and Mohammed Thiem at Tuskegee, as well as structures, which is led by Connor Skelly here at Clemson. Our project manager is Julian Thompson from Tuskegee, and our chief engineer is Alex Miner from Georgia Tech. So this table shows our budget in terms of what we've already spent and how much we have remaining. So far, we've spent the most of our budget on controls, so we can start testing our systems. We anticipate spending much more on manufacturing next semester. We have a good amount of margin built in to our budget so that it'll be spent to fill in any gaps that we have. So there's an overview of our Gantt chart. It shows we're trying to finish manufacturing early on and then continue testing our subsystems as we begin integrating them into our UAS. So far, we are on track to meet all of our deadlines. So now we're going to shift focus and cover our final design and UAS subsystems. Pictured here is an isometric drawing view of our UAS that includes all major dimensions, including our wingspan and total length from nose to tail. It includes our root chord length, as well as our tip chord length, and the dimensions for our empennage, vertical and horizontal stabilizers. So to give an overview of our fuselage, we're planning for our fuselage to be manufactured in 2 halves, which will be made of carbon fiber and include a Kevlar reinforced belly. Towards the front of the fuselage, pictured on the right of that image, there will be a cutout that will house our camera. There are also 2 payload doors and an access hatch that will be designed into our fuselage. To provide everyone with an overview of our internal structure, this will serve as our main focal point for component integration and will be epoxied to the inside surface of our fuselage skin. There will be 4 attachment points, one for the polar motor, wing spars, tail boom, as well as payload. The structure is also sectioned to include a payload and controls bay. Shown to the right of this slide are our internal component and truss structure designs. Our initial concept and truss structure designs. We plan to have our truss structure, which is shown at the top right of the slide, laser cut from 1/8 inch ply. We're working right now on reshaping the ends of our structure to match the profile of our fuselage. It'll be extended a little bit further into the nose of our fuselage for rigidity as well. So this is an outline of our wings. Each wing will be 4 foot in length. The airfoil profile that we've chosen is the SD7026. They'll be reinforced with 2 dual carbon fiber spars, one that has a 0.75 inch outer diameter and one that has a 0.55 inch outer diameter. The wings will be manufactured with a foam core and will have a fiberglass skin. For our empennage assembly, we've selected symmetric NICA 12 airfoils for our horizontal and vertical stabilizers. Both stabilizers will have a foam core and a fiberglass skin that they will be fastened together using a fixture similar to the one that we used to manufacture our glider. They will also be reinforced with carbon fiber booms similar to our main wing. So the next couple of slides hit on our UAS subsystems, beginning with our wing attachment. Our current design plan is to have each wing spar slide in support tubes that are integrated into our support structure. The wing spars will be secured within these support tubes via pins. So concerning our vertical takeoff and lift capabilities, we've designed a fixture that will connect to both wing spars. This fixture will have a removable lower base to help improve transportability. So as shown in this slide, we will have a quad boom that will be attached to each wing via this fixture that you see in the 4 images on the right of the slide. Each quad boom will have a cowling on the end, which will house the quad motor in order to improve aerodynamics. So our tail boom will be secured inside of our fuselage via our internal structure in a similar manner as our wing spars. The boom will be secured in a housing unit that is integrated into our fuselage structure. The boom will be secured via pins in a similar manner that the wings will be secured. So on this slide is an overview of our primary structural components, which include our wing spars and booms. Outlined are our dimensional properties such as outer diameter and inner diameter, assumed static loading, design goals, and the methods that we use to achieve each of those goals. I'm going to turn it over to Alex at Georgia Tech.
Hi, so I'm going to finish out the presentation, starting by talking about the control system. So this is our power budget. We plan to use 5 amp-hour batteries. 2 of them will be for the puller and 1 for the quads. We decided this configuration so that we will always know our flight time based on the puller, and if we use the quads too much, they won't take energy away from the puller motor and give us an unknown flight time. We're expecting, if we fly at a 65% throttle, a flight time of about 30 minutes. The hover quads only give us a flight time of about 4.6 minutes at full throttle. We don't expect this to be a problem because we don't intend to fly at hover the whole time. It's only for short periods of time during payload deployment and also potentially takeoff and landing. So this is an overview of the hardware components. I'm not going to go through all of these, but basically we're using a Picksock 4 with a Raspberry Pi for computer vision or camera vision and analyzing images to identify people. We also have some sensors that we're using, such as LiDAR, our GPS signaling antenna, and then also our radio controls. This is just a quick layout of how the controls hardware will be in the fuselage. So as we saw before, we have an upper bay for our controls hardware within the structure. So here you can see that the Raspberry Pi will be towards the front, and then we have the Picksock 4 as number 2 in the back, and then our LiDAR, Raspberry Pi camera, and our airspeed sensor. So to talk about the wiring diagram, we're starting with the wiring recommendations that are given by Picksock 4. This is the power management board that comes from with the Picksock 4. Basically, this is what you attach all of the motors and ESCs to, as well as the batteries and the BEC for our servos for control surfaces. This is our wiring diagram. It's kind of hard to see here, but the breadboards represent some of the boards that were not present in the software that we used to make this diagram. So at the bottom, we have the power management board with the servos connected to it, and then we have the puller motor with its ESC connected to the power management board, as well as the battery and the BEC. And then we also have the quad motors attached to the 4-in-1 ESC up to the right. Then at the very top, we have the Picksock 4 and the Raspberry Pi to the left of that. This basically just shows the layout, and once we start assembling our control system, we'll follow this diagram to make sure that everything is wired properly. So now on to propulsion. Our quad motors and propellers are the T-motor F1000 long shaft motor. We are going to use a 14-inch propeller with this for the quad. It will give us a thrust to weight ratio of about 1.8 with some factor of safety built in. This is going to be used with a 4-in-1 ESC for controllability in our PICSOC 4. These are just some basic specs about the motor. Our testing will go into more detail on this and make sure that these numbers are actually correct, and we'll have a specific value for our motors. This is our puller motor. So we're using the Scorpion S2 with a foldable carbon fiber propeller that's 16 inches in diameter. It has a thrust to weight ratio of about 0.85. And again, some specs on this: about 85% efficiency, drawing 67 amps at max throttle, but we intend to run this at about 65% throttle. So now these are the quad motor cowlings. We mentioned these before, but this is our preliminary design for them. We know that having the quad sticking off the wings will cause some drag effects, so we wanted to make this 3D printed part that we could use not only to house the motors, but also to attach them to the quad booms and then decrease drag. So basically the motor will sit in that cup right there. The propeller will be up out of the fit, and then the extrusion off the back is what will fit into our quad booms that are attached to the wings. We're planning to try to hollow them out, and we'll also add some holes to the cup where the motor is going to be for cooling. Now to our testing and validation plans. So we've already built our glider and did some preliminary flight tests this week. Our first flight test went pretty well, but we broke the nose because it was made out of just foam. So we repaired it and ended up flight testing again yesterday, and we were able to have a good gliding flight, both from ground level and then also from a height. So at this point, we are working on repairing it because we did break a wing, similar to one of the other teams where they broke the wing where the spar changed from carbon fiber to a wooden dowel. Ours broke where our spar changed from metal to wood. So we're working on repairing it, and then we'll do some more flight tests, and hopefully next semester we can also use the glider for integrating some of our servos and testing them as well. We learned a lot from building this glider, including how we're going to attach the tail boom as well as the quad motors and the wings. So it was very useful to build the glider. So for our aerodynamic testing, we're going to do CFD and wind tunnel tests. The wind tunnel test will be mostly for flow visualization around the quad booms to see their effects, and then CFD will be done to verify what we're expecting for the airfoil as well as drag that we'll get from the fuselage. This is just a slide showing a preliminary CFD model on an older revision of the fuselage that we had. We haven't been able to start CFD yet because we're having trouble with software access, but over break and next semester we'll be finishing our CFD to validate all of our aerodynamic choices. So we're also going to need to do some payload system tests. This is an older diagram of showing roughly how the payload is attached in the fuselage. We want to make sure that all of the components of the payload drop system, including the serverless release mechanism and the door system, work as expected. So we'll do individual component tests and then also test the whole system together. And then we also need to test the minimum height to drop the payload where the parachute will still open. We've done some FEA already. This is an example of FEA on the quad boom. So basically those two center pieces are how it's mounted to the wing, and then the forces are on the two tips of the boom. The deflection here is exaggerated. It's only about 3.5 millimeters of deflection on both sides, or maximum deflection on that one side. The reason it's an uneven distribution is because of where it's mounted on the wing. The rear motor is further from the connection point than the front motor. So we also need to test our control system. This picture here is of a quadcopter test bed. So we plan to invest in a small quadcopter that is inexpensive but can be used to fine-tune our control system, because we want to make sure that we can control a quadcopter before we try to put it on our plane and risk burning out any expensive motors. So that's something we're going to be working on over break and next semester. We also need to test each of the individual components upon receiving them, and then after wiring and soldering them to make sure that components are working as advertised, but also we're not having any problems with soldering and wiring. We can also use this to test our human detection system and acquiring flight data. So our propulsion system test will be using the RC benchmark system at Tuskegee. We'll use this to get some data on RPM, torque, efficiency, thrust, and just overall seeing how well the motor and propeller combination works. And then we can also connect them to the ESC and maximize the thrust to see when things will start to shut off or overheat. Now on to our manufacturing plan. We intend to make most of the components at our respective schools. However, we're considering making the fuselage at EVCC since we want it to be carbon fiber. And then all the finalizing of that will be at Georgia Tech. We'll also make the wings at Georgia Tech. The horizontal and vertical stabilizer will be made at Clemson. The control system is being worked on at Georgia Tech, and then the quad propulsion system will be done at Tuskegee. All of the components will need to be shipped to Georgia Tech, where we're doing the final integration, and we're hoping to have all of them done by mid-February. This is a bit of a stretch goal, but having it early on will give us time to test each component individually and then have time for flight testing. So our manufacturing plan basically decided where each component would be assembled based on the location of the university and the capabilities for manufacturing that those universities had, as well as past experience of group members. We wanted to give everyone a chance to learn some new things, but also make sure that we were reasonable in what we were assigning to people so that everything would get done correctly. Primarily, we'll be using a 3D printer, laser cutter, and CNC foam cutters to create our components. We also need to work on some tooling for attaching all of our components. This is something that we learned with the glider, making sure that everything's lined up properly before epoxying it, and then making sure that we have it secured while it's drying can help make sure every component is integrated properly. So, one second. Sorry about that. So each component will have a subsystem and an integration plan and manufacturing plan that tells essentially exactly what we're expecting from each subsystem when it's created before it gets shipped. So we're working on these plans right now, and that way we can make sure that every component arrives at Georgia Tech as expected, and we can easily integrate them all into each other. We'll test fit all the components and make sure that there's a smooth mating, do any troubleshooting that we may have, and then run static tests on the full assembly to make sure that it is structurally sound before we do any sort of flight test. So that concludes our presentation on CDR, and we'll open it up to questions.
Yes, this is Todd Harless from Boeing, and I saw that you had done some pretty good work to get an estimation on the power demand of the motor through the ESC, and it looked like even perhaps some exceptions or faults were obtained. I think it was on the motor itself that it looked like you had a cutout. If you go down some more, I was just curious, does this get rolled back if you were to see, I think it's on the one where you were showing the test stand and you talked about how you found max power limit and how to shut it off. And right there, yes. Is this rolled, I'm just curious from a systems engineering process point of view, when you find these sort of limits, do these get rolled back into the operations and sequences of what you want the vehicle to do to understand if this is something that the vehicle can handle, or is it just something that you find right now and it gets rolled in later to understand if the vehicle operations will be satisfactory for the mission?
So it's more of a maximum test for sort of like breaking a boom to see at what point it will break. Not necessarily that we're trying to run it at that max thrust or RPM before it will start to shut off, but just that we want to make sure we know what that limit is so we can not approach it.
And that's what I was after. Do you guys, have you studied that at the operational level and model level to understand if the vehicle will ever encounter that? And if it does, do you have abilities to understand how to handle those scenarios, or is that something that is going on in the future?
Right. So we haven't done that yet. As of now, we're not expecting to have to run at 100% throttle for our polar motor. But once we get to that point of flight testing, we'll determine if that's something that we have to, and then figure out a plan for handling it.
I see. So it's in the testing phase itself, after parts have been built, that you'll start to understand if it's successful or not. Okay.
It's also highly dependent on our final weight, which we can't be 100% sure of right now since we haven't started manufacturing. So we end up with a heavier weight than we're gonna have need more thrust from our polar motor, which is the limit.
Yeah, absolutely. I understand. I'm just curious at a very higher level, systems modeling level, if we understand if this is to occur, do we have operations in place to know how to handle it, or is it something we will have to tackle if it occurs?
Right. Yeah, that's something that we definitely need to look at, and it will be later into the testing phase.
Okay. Thank you.
Hey, Branko Lakic from Boeing here. If you go to your page 10, okay, so I understand, if I understand right, your position number 3, is it leading towards the engine mount?
No, position 3 is for the tail.
Okay, so position 1 would lead to the engine mount, am I right?
Correct.
So, is there a reason why you should not just make a sleeve and continue your tail boom straight through that centerpiece? Which, by the way, it's very smart and efficient. I really like the fact that, you know, your wing, your tail, and your power plant is all attached to a structural machine part, and then the rest of the airplane and your payloads is just hanging off from that. So that is very efficient. What I would suggest maybe to continue the tail boom straight through that box and then attach them engine mounts on it. So I think you may have more efficient structure like that.
Yes, that's actually something we're considering. It's just the update didn't make it into this presentation.
Another one of the reasons was to hold the controls in the bay that she is showing, and if you were to run that sleeve all the way through, we wouldn't have nearly the amount of room to house our controls.
But we are considering, so these right here, these attachment points, we are going to run these all the way across for our wing spars because it'll just make it a lot more structurally sound to have 2 attachment points for one main spar within the fuselage. We can look into attaching the tail boom to the quad or the puller motor mount because that will be more structurally sound. We have to be conscious of our controls that sit inside this bay right here.
And then just one more comment. You said that you're planning to make your fuselage out of carbon fiber and reinforce it with a Kevlar. In this particular scenario, your fuselage will only carry the abuse loads. So you may be very careful how much weight you put in it. Maybe you want to reinforce it only in the front area for the impact, but you know, really the fuselage shell doesn't carry any loads in this scenario.
Right. So our plan, we talked to EVCC, and based on weight, we decided not to try to put a large amount of Kevlar. It was going to be the 2 carbon fiber halves and then a very small tube that we can glue on after with similar resin as the carbon fiber layout.
That's all.
Thank you.
Okay, cool. Let's keep on moving. We've pretty much gotten back on track here. Maybe it's a couple minutes behind. So thank you everybody for that. Once again, if you guys have feedback for Team 3, feel free to fill out the survey that Kathleen had sent out yesterday, I believe. And then you guys driving, right? Yes. Go ahead and do share on WebEx. You should be able to do. No, you're not sharing yet. Go up there and then go up to the top. Yeah, click that. And then go up to share up to the top left. And then you can just do share Adobe if you want to do app.
Share what?
Just do share screen and screen 2.